Hello, welcome to another CASIM video tutorial. Today what I'm going to do is connect my homemade breadboard Arduino and DIY force sensors to Supercollider and then build a QFM or hybrid frequency modulation synthesis engine in Supercollider. In the previous video we used pure data for our synthesis engine. And by way of contrast, I'm going to use Supercollider. The two programs are free, open source, very powerful, but completely different programming paradigms. Pure data is a graphical programming environment or language, wherein we connect virtual objects with virtual patch cables, and those objects perform specific functions, a variety of functions. The concept is the same in Supercollider, but the programming language is object-orientated, which means we type our code, write functions, pass messages to classes of objects. This is not a Supercollider or programming tutorial. I'll be doing that at a later date. I'll be looking at Supercollider in detail, how we can use it for audio DSP. But suffice to say that we're going to use the same synthesis algorithm. So conceptually, Supercollider should be easier to grasp in that regard. And what is the synthesis concept? Well, we want a sine oscillator whose frequency is a center frequency plus the output of another sine oscillator, and we've seen this in pure data. Sine oscillator, and that oscillator's, the modulating oscillator's frequency is the carrier frequency multiplied by a ratio, and the output scalar or depth multiplier is the center frequency multiplied by ratio multiplied by index times R times I. And that is the pseudocode that we're going to implement in Supercollider. And the way we create audio functions is we're using these curly braces, and we say function.play. And inside that function we place any number of unit generators, which is Supercollider's name for a class of objects that generate control or audio signals. We're going to put a bunch of unit generators inside function.play, and we will hear the results. For example, pink noise .ar. .ar means I want audio rate, so I can hear it, as opposed to .kr, which is control rate, and I wouldn't hear anything. And I want to multiply, scale that, so it's not too loud, 0.4. I need to boot the server. I can do that by right-clicking on this little green display here, or I can go language, boot the server, or I can do Control B, Control or Command B. Many different ways to do things. So let's hold Shift Enter. What that does is it executes, runs the code, and we hear pink noise. And to stop audio processing, I hold Command or Control, period. Okay, that's all working, just testing for echo there. So this is the function that we need to put our unit generators inside. Consequently, I'm going to be writing many lines of code, or several lines of code. And in order to run those all in one block, I encapsulate them in parentheses, then write my functions in here. Write my functions in here, and I then hold Control Enter or Command plus Enter to execute that code. So let's see what happens. Let's just type some code. So I need a sine oscillator at audio rate, and I want a frequency value here as its first argument in brackets. Let's say 340. and I want want to scale that amplitude, multiply by 0.3. Don't get it too loud. And now I hold Command or Control Enter. And we get a mono sine tone. Let's look. The meters, Control M or Command M. Nice little graphic GUI object. Run that code again. See, we're going out mono at the left channel. So back to our FM algorithm. Let's focus. This frequency value here has something added to it. Let's do that. And after the 340, after the frequency value number, type enter. Put these on separate lines. I want to add the output of another sine oscillator. And his frequency is the carrier frequency multiplied by a ratio value. I'm just typing ratio here. These are arguments that I'm going to have to add to my function pretty soon. And then the multiplier is, close brackets there. This is my modulating oscillator. This mul applies to the carrier oscillator. So I want to multiply that. I'm not going to use this syntax. I'm going to make things a little clearer. So the multiplier for my modulator is the center frequency, which at the moment is 340, multiplied by ratio. I keep writing ration, multiplied by index. So by doing that, I've identified which values I need to plug in to my function. And we write these as arguments. So I've got a center frequency, I've got a ratio, and I've got an index, semicolon, to end that declaration of arguments. So now we can plug these into our little equation here, or little graph. So the center frequency is CF. Whenever I see 340, I'm going to say CF. So let's initialize that center frequency to 300. What about the ratio? Multiplied by the ratio. Well, for now, as we did in the pure data example, we'll set the ratio to 1. And the index we'll set quite high. We'll set to 500. So to recap, we have a carrier sine oscillator at a fixed center frequency, which is then modulated by the output of a modulating oscillator. And his frequency is a function of the center frequency multiplied by ratio, and the output scalar for the modulator is the center frequency multiplied by the ratio multiplied by the index. And then we're scaling the whole thing. We're scaling the carrier by 0.3. Let's see if that works. I've missed a bracket somewhere. Yes, I have. Or braces. No. Let me see this handy little debug window. Oh, I didn't write the word index for my argument. I didn't name my argument. Ooh, yeah, another error. I suppose errors are good. Let you see what you must not forget. It won't run the code if it sees a syntax error. So what I forgot to do was declare or set the method to sinos. I didn't know whether it was audio rate or control rate or demand or whatever. It should work. And it does. Let's change the index to 50. change the ratio to 0.75. Sounds like FM to me. Now I need to stop, I need to do command or control period each time I run this code before changing any of these arguments. That's not very convenient or dynamic or interactive. Let's set the index to 5. Okay. How do we expose those arguments to use for use outside the function? Well, we need to give that function bunch of unit generators a name, and the letters A to Z are reserved as global variables. So I've named my function.play and called it x, which means I can now say x.set center frequency. Sorry, I need to ensure that it's a symbol or string. Center frequency, comma, 200. I'll run my function, and now while it's running, I can change those arguments, and I can change them all. And ultimately, that's what I want to do with the data from the force sensor. So that's basic FM, the most basic FM synthesis algorithm you can think of. But we're aiming for quantized frequency modulation, QFM. And what difference does that bring to this algorithm here? Well, it's quite simple, really. I want a sample and hold oscillator, and in Supercollider I can use the latch class, encapsulate that whole thing in brackets. But what latch needs, or sample and hold needs, as we found in pure data, is we need an impulse or a trigger. So I can use a low frequency sawtooth oscillator at audio rate, and the frequency value is the frequency of the modulator, which we recall is CF multiplied by R, and then we multiply that by, what am I going to call the rate or the ratio? I'll just call it TR, which is trigger ratio. Let's implement that in our FM function. Go. So I've spotted my glaring error. I was rushing at it a little bit fast. I was a little too keen. My algorithm is wrong. I don't want to pass the entire signal, the entire FM signal, through latch. It's the modulator that is latched. So I'll get rid of latch.ar there. And it's this modulating oscillator. This is my carrier, sine oscillator, whose frequency is a function of the center frequency plus the modulating oscillator, and it's that passes through latch. So that's the modulating oscillator. I've probably got these brackets the wrong way around. Let me see, latch. So yes, I have. Yeah. So latch has two elements. It has the input signal, which is my modulating oscillator, and then it has a trigger. Okay, fine. What I need to do is pass the modulating oscillator through latch. And this mul value here is the overall output. So just tuck him out of the way. Pass the modulator through latch. That's my input signal. Now I need a trigger, and I'll use sawtooth oscillator at audio rate for the time being, and his frequency is going to be CF multiplied by ratio multiplied by trigger ratio. Have I got enough parentheses? No, not yet. Yes, now I do. Happy days. Let's try changing some of these variables or these arguments from outside. So just to recap, this is my carrier oscillator, this is my modulator oscillator, and his arguments. An inside latch, I need two elements. I need the input signal, which is going to sample and hold, and I need a trigger. That's why I added trigger ratio. Let's run that. So there'll be some noise in the background so we can hear how these things change. Set the ratio to something uneven. I'll set index a little higher, and I'll set the trigger ratio and it's fun to see what's happening. Use the frequency scope object. So what I'm going to do now is connect my Arduino and DIY FSRs to Supercollider, and we will use the Arduino SMS class. Like most audio software, Supercollider comes with a bunch of externals, libraries, which are called quarks. Let's just run quarks.gui. And an extensive list. Look at that, there's about 150, maybe 100 there. And this allows us to grab data from the Arduino. It's possible to do it without using an external or a quark, using a native serial port class. Up until I think 3.8, serial port was only available on OS X and Linux. Now, thankfully, it's available on Windows. I don't know how stable it is. It's a recent update for Windows Supercollider users. It's possible to do it using serial port, but I've just kind of got used to Arduino SMS. So we'll look at that in the next video.